Hello everyone and welcome to Container Day. In this session we are going to cover Kubernetes networking on AWS. My name is Mike Stefaniak. I'm a senior product manager for Amazon EKS. And I think it's important to note that while my title is a product manager for EKS, really my job is to make sure that AWS is the best place to run Kubernetes. And networking especially, it can work with EKS, but given EKS is just upstream Kubernetes, you can also use it if you're running your own cluster on EC2. So in this session, we're going to dive into the unique approach that AWS has taken to simplify Kubernetes networking and some of the upcoming features, as well as a quick demo. So we're going to cover a brief overview of Kubernetes networking. You could probably spend days or months or even years learning this topic and never quite mastering it, but we'll do a quick overview. We'll talk about the Amazon VPC CNI Plugin, the architecture and some of the features, and then we're gonna dive into a long-awaited feature, security groups for pods, and do a quick demo of that. And then we're gonna cover the upcoming roadmap for some of the other networking features. Networking in Kubernetes. Like I said, it's a big topic. We're gonna try to do it in one slide. The Kubernetes networking model has three main requirements. It's that all pods can communicate with other pods without using NAT. It's that all nodes can communicate with all pods without NAT, and that the IP that a pod sees itself is the same IP address that others see it as. So every pod gets its own IP address, and this means that you don't need to explicitly create links between pods, and you don't need to deal with mapping container ports to host ports. It creates a clean, backwards compatible model where pods can be treated much like virtual machines or physical hosts from the perspective of service discovery, naming, load balancing, application configuration. So this model is less complex overall, but it also makes it easy to enable low friction porting of apps from VMs to containers. If your job previously ran in a VM and it had an IP address, you should be able to move it relatively easy to Kubernetes. Now, Kubernetes itself doesn't implement this model. They leave it up to plugins based on the container network interface, which is a CNCF project that consists of a specification and libraries for writing plugins to configure network interfaces. CNI really only concerns itself with the network connectivity of containers and configuring the network between the network and the pods network. And as long as these networking requirements is met, plugins are really free to implement the network stack as they desire. And so when we started building EKS 2 years ago, we looked at, what is the best way that we can build a plugin for Kubernetes networking on AWS? And the approach that many people are familiar with and a lot of plugins existed were overlay networks is an approach you can take. And an overlay network implements a common network address space across the entire cluster which containers can communicate. In an overlay mode, a container is independent of the host's IP address range. And during node-to-node communication, tunnels are established and all packets are encapsulated. So this networking mode removes the dependency on the underlying network. And this has some advantages for sure. Portability is definitely one. You can run, given that there's no dependency on the underlying host network, you can run it in the cloud, you can run it on premise. A few other common advantages are if you're in an IPv4 constrained environment, you're not consuming the IP addresses of the underlying host network. It's a separate network running on top, hence the overlay name. And then lastly, the pod density isn't tied to the instance type. However, when we were looking at this, there's also a number of cons that come with overlaid networks. One of the big ones is it's hard to debug. It's an additional failure mode to the application stack, and it increases the surface area for networking issue that could affect every application deployed on the cluster. Some other downsides are that external applications of the cluster can't communicate with the pod directly. You get reduced effectiveness of VPC native tools like security groups or flow logs since they expect traffic at the wrong level of abstraction. Connecting to on-premises networks can be more complicated because you don't have that direct integration with the VPC. And then another big one is that scaling challenges we've seen with overlay networks. Encapsulation requires node resources that can't be then used for your applications, and then you also get increased network overhead when using an overlay. Based on that analysis, we decided to take a different approach, and we built the VPC CNI plugin, which enables us to integrate more tightly with VPC resources and provide an opinionated VPC native networking solution for EKS and Kubernetes on AWS customers. With this plugin, pod networking has the same performance as the VPC network. You get the same performance as a raw EC2 instance. You also can scale to 1,000 plus nodes without networking being the bottleneck. Networking is simple, it's secure, and it's familiar to AWS users. You can directly reach pods from external to cluster applications. This allows us to do things like direct to IP ingress from load balancers, and you remove the extra hop of hitting the node itself. You get simple direct integration with other VPC features like flow logs, transit gateway, direct connect. And then finally, we decided to open source this solution. So it's not just an EKS thing, but for any Kubernetes on AWS users. And we're going to cover the architecture. So by simplifying the network stack, the CNI plugin has really lowered the barrier of entry for Kubernetes on AWS and making it more accessible to those users. So let's see how it works. We have two nodes here in our VPC, and every node is going to get an elastic, at least one elastic network interface provisioned for it. And you can see that the CNI plugin is going to make a bunch of EC2 API calls. Let's just get all of this open here. And so every time you need to add a pod to the instance, the CNI plugin is going to check if there's any available secondary IP addresses. And if it's not, it's going to call out to EC2, add an additional ENI or a secondary IP address. And every pod is getting a real VPC IP address. It's important to note with this architecture that planning IP space, IPv4 space in your VPC is important, as you want to make sure that your VPC has enough IP space at the beginning for application expansion, although we will cover an option in a minute if you're using an existing VPC that doesn't have a large primary CIDR block. And this plugin is open sourced on GitHub, so you can see the link below there. We strongly recommend that you upgrade to the latest version, as we've been releasing a lot of new versions recently with a number of features and fixes, including more configuration options for VPC peering, defaulting to random fully for iptables rules, and we've done a lot of optimization of the EC2 API calls to reduce the number of those. I mentioned that support for advanced networking architectures. So in this case, a common problem we see is that customers may have a small primary VPC CIDR block. And because your pods are using real IP addresses, you may quickly run out of those IP addresses. So we have a feature, it's called custom networking within the CNI plugin. And what that allows you to do is you can associate additional CIDR blocks of IP addresses to your VPC. And it's essentially very similar to an overlay network. In this case, it's just a reserved range. It's the 100.64 and the 198.19 ranges that you can add to existing VPCs. And these are exclusive ranges that can be used just for pod networking and not for direct communication between the VPC, VPN, or other external networks. So if you see in this example here, you have one subnet using the primary VPC IP space, which is over here, and you have your node that has the primary ENI. But now you have your pods, similar to an overlay network, where the pods are running in a separate subnet from the node. In this case, you have a similar experience, but it's actually using a separate real IP range in the VPC. So in this case, we have our pods using the 100.64 address space, and now you have a network setup where you're not consuming any IPv4 address space. So you can see the link below there if you want more details on how to implement this feature. Now let's talk about security groups. By creating a CNI plugin that integrates directly with VPC, we can take advantage of VPC native features. And coming very soon, you will be able to assign security groups directly to pods. And a couple of the use cases we've heard from you on why you wanted this feature is to maintain security in multi-tenant clusters by running applications with different network security requirements on a shared pool of compute resources. You can also control network access from pods to other AWS services outside of your cluster, like RDS. And then the last one we hear often is, if you're going on application modernization efforts and you're migrating applications from EC2 to EKS or Kubernetes, you can bring along those security groups with you rather than having to re-implement those rules as Kubernetes network policies. Now, we did release a feature last year called IAM roles for service accounts, which solves this pod level security challenge at the authentication layer. But we've heard that many of your compliance requirements also mandate network segmentation as an additional defense in depth step. So by assigning security groups for pods, it makes it easy to achieve that network security compliance in shared clusters by running applications with different requirements on the same nodes. And here we're going to show a quick before and after picture of how your application might look without pod security groups and with pod security groups. So without them, you might have to spin up separate node groups per application. And then you have this complicated set of taints and node selectors to make sure that your applications land on the correct nodes. And this is a problem that is hard to do at scale. As you have more and more applications, you have to create more and more node groups. And with those more node groups, they become underutilized. And you're not really using Kubernetes as it's meant in this case, which is this shared pool of compute resources. So when you can assign security groups directly to pods, now we can just have a single node group. And application A might have to access RDS, and application B might have to access Elasticache, and they can live on the same node, but only A will access RDS and only B will access Elasticache. Behind the scenes, it's to make this all work, it's leveraging a feature called ENI trunking and branching. It's a feature that allows for many network interfaces known as branch ENIs from the VPC to be multiplexed through a single ENI known as the trunk ENI attached to an instance. And this allows for greater scaling of multiple ENIs on a single instance. And it's supported on most of the recent instance families based on the AWS Nitro hypervisor. So without further ado, let's actually see how this works, because I imagine that's what most of you want to see. So I have a cluster over here, and to make it simple, I just have a single node in my cluster. And in fact, we'll show you the labels, and you can see we've added this additional label called this has trunk attached, and this is how you know we've attached the trunk ENI to the instance. So to actually apply security groups to pods, what we've done is built a new custom resource definition, and we'll show you an example here. So if you're familiar with network policies, this probably looks familiar to you. It's the similar pod selector where we're going to select pods based on labels. You can also select it based on service account labels. And in this case, we want to assign to any pod that has a label of key, role, and value backend, we want to assign these two security groups. The security groups in this case are, the first one is the cluster security group. So this is going to allow the pod to communicate with core DNS that is running without a branch ENI. It's just a regular secondary IP address. In this second security group is, ahead of time, I went ahead and created an RDS database. I created this security group, and I added this particular security group to the ingress rules of the RDS database security group. So essentially, this is the security group you'd want to apply to any application that requires access to this RDS database. So let's go ahead and apply this to our cluster. And now what I went ahead and did is created a simple application. So I containerized this simple Python application. It's just connecting to the RDS database, running a simple select version query and printing the results. If it can't connect, it's gonna print out an error message. And so I have this in a simple deployment here. This is the image that I had pushed to my registry. You can see this is my database address. I won't cover this in too much, but I'm actually using the RDS IAM authentication feature here. So for defense in depth, I'm actually using IAM rules for service accounts to provide the authentication. And then on top of that, I'm doing it at the network level with a security group. So this is my manifest that I can apply to the cluster. And you can see here that we're assigning it the role backend, which will match the rules we set earlier. And let's go ahead and describe this pod so we can see what's happening. And if you can see, there's a webhook running on the control plane that injected this resource request. And we're essentially saying, because this pod requires a security group, it needs its own branch ENI. And then you can see we annotated it with, the server annotated it with, here's the branch ENI it should use. And when this pod gets scheduled, the CNI plugin is going to see this and say, okay, I need to wire this up to the branch ENI. And if we look at the logs, we can see success. I was able to connect to the database. Now, let's show I have another one. In this case, it's all the same, except I'm not supplying the label. And this won't match. And keep in mind, I only have a single node here, so think of it like a shared compute pool. And if all goes well, this pod should not, even though that's on the same node, it shouldn't be able to connect to the database. So, and there you go. Database connection failed due to timeout expired. So now we have two applications, one that requires access to RDS, the other that shouldn't have it, and they're both running on the same set of nodes. Okay. That's how it works. Some other things coming on the roadmap, because we do have a very full networking roadmap. We plan to simplify the custom networking feature that I talked about earlier that'll make it easier to use. I didn't touch on load balancing much, but two highly requested features are NLB IP targeting and ALB ingress grouping. These are both coming very soon. There'll be a new controller that we're releasing that covers both of these use cases. We'll have a VPC feature that we're integrating with towards the end of the year that will allow us to have higher pod densities on smaller instance types. We will continue to migrate the IP address management functionality out of the existing plugin into the VPC resource controller that's running on the control plane. So as part of this security groups for pod feature, this VPC resource controller is the one that's actually handling the ENI trunking and branching, which is running on the control plane. And we do plan to migrate all of the IP address management to this controller in the fullness of time. And then the last area where we'll be investing heavily, and this is really where we believe is the real solution to IP exhaustion compared to an overlay network, is IPv6. So IPv6 is a large area, and in that linked issue, I explain all the different milestones we have. But ultimately, we want to do is have a world where you can have IPv6 only pods that running in an EKS cluster. I put a few resources in here where you can learn more: the EKS documentation, the CNI plugin, which is open source, I'd recommend looking at our original CNI plugin proposal, which goes into more details of why we decided to build a native VPC integrated plugin rather than a different approach. And then I linked a couple of blogs here which has some more info on how cluster networking works in EKS and options for conserving IPv4 while using the VPC CNI plugin. Thank you very much. If you have any questions or suggestions, you can certainly leave them in the chat. We'll stick around for a little bit. Also, definitely visit our virtual booth during KubeCon EU 2020. Thank you.